Hello. In the previous lecture, we discussed about the different types of deformation mechanisms like quasi-static deformation and dynamic deformation. So, deformation are of two types. One is quasi-static and one is dynamic. So, today we will discuss about elastic wave and is the types of elastic waves. So, that comes under the dynamic deformation which involves stress wave propagation So, stress wave can be classified into three categories that we discussed earlier: elastic wave, plastic wave and shock wave. So, in elastic wave is a low amplitude wave. The elastic wave is a low amplitude wave. It has low amplitude and the particle velocity is linearly proportional to its amplitude. Particle velocity is proportional to its amplitude. And the material particles, as we know, those material particles in a body oscillates about its equilibrium position. If you assume this is the equilibrium position, so it oscillates about the equilibrium position, and if the amplitude cross a critical limit, that is the elastic limit, if the amplitude is greater than elastic limit, then the pulse will decomposed into elastic and plastic waves. So, today we will discuss basically elastic wave and its classification. Oh, sorry. So, this is not shock, shook. So, this should be shock wave. I am sorry about that. Shock wave. So, in a previous lecture we discussed about the elastic wave equation in a spring or helical spring or in a string. So, today we will discuss elastic wave in impact problems. So, we will discuss elastic wave in impact problems, and so we will take an example of a striking bar impacting on a long cylindrical bar. So, this is a striking bar on the left hand side and this is a long cylindrical body, or we can say a bar. It is a slender body. So, the striking bar will hit the cylindrical bar, long cylindrical bar, with a velocity v, which is the impact velocity. So, we are assuming here only elastic, deformation, and no permanent or plastic deformation. So, if we impact with the striking bar So this striking bar will hit the long bar and at a time t, time equal to t. So let's assume that the wave, the front of the disturbance, the wave reaches at the point x, and that section we call it as a AB, that is the front of the disturbance or wave, the section AB. And if we take another section A prime B prime at a distance delta x, so and then we can consider the small element, infinitesimal element, which has a displacement u. Also, the one assumption is that strain and inertia in the transverse direction is neglected. In the transverse direction is neglected. So we will now consider this infinitesimal element AB, A prime B prime. So this element, if we see the forces, or we'll make it a little longer. So this is the element A B, A prime B prime. That's a small element in the bar, and then we can see that the compressive forces A sigma is the stress multiplied by A area is the cross sectional area, of the cylindrical bar. And deeper into the bar at the section A prime B prime, the force will have an additional increment with A multiplied by sigma partial of sigma with respect to x delta x. As we know, the sigma stress is a multivariable function, thus that is partial of sigma with respect to x. So now we will apply the Newton's law of second law. So applying Newton's second law on that segment, Newton's second law on so that we know that F equal to ma, and the force will be equal to A sigma minus A multiplied by sigma plus partial of sigma with respect to x delta x, which will be equal to A, rho A is the cross section area, rho is the mass density, and delta x partial of u, second partial of u with respect to t is the second partial of u with respect to t is the acceleration, and mass is equal to cross sectional area multiplied by delta x, the thickness of the bar, and mass density rho. So now we can simplify this expression, so that will give us partial of sigma with respect to x, which will be equal to rho second partial of u with respect to t. So as we can see, the area on the left hand side and right hand side, and will cancel out. So we can now use the Hooke's law, that is for linear elastic solid. So if we apply Hooke's law, that is sigma is equal to Young's modulus multiplied by strain epsilon, and then from our earlier equation, from this equation, we can have partial of E epsilon with respect to x is equal to rho multiplied by second partial of u with respect to t, and then we know the strain can be expressed as partial of u with respect to x, which is also a multivariable function. The displacement is a multivariable function, and that will give us E partial of u with respect to x is equal to rho second partial of u with respect to t, and this will finally give us E second partial of u with respect to x rho second partial of u with respect to t, which we can write little differently as second partial of u with respect to t is equal to Young's modulus divided by mass density multiplied by partial of u second partial of u with respect to x. So this is the wave equation for elastic wave propagation. Wave equation for elastic wave propagation. So while a striker bar impacted a cylindrical thin bar, so this is the problem we took, and then we finally derived the wave equation for elastic wave propagation, which is the double partial of displacement with respect to time is equal to Young's modulus divided by mass density multiplied by double partial of displacement with respect to x. So from the earlier discussion in the earlier lectures, and also from this equation, we can say that the velocity of the wave c naught can be expressed by square root of the ratio of Young's modulus divided by mass density. So we can have the velocity as the square root of the ratio of this Young's modulus and mass density. Now we will discuss a little bit about the types of elastic waves. We will mostly focused on 2 or 3 of them, but there are several of them. We will just touch little bit of that, those classifications. So basically the classification is based on how the motion of the material particles are related to the direction of propagation of the wave themselves and on the boundary conditions. So when we call this particle, so particle is not atom, particle is not atom, because the motion of atoms are not straightforward. Motion of atoms are not straightforward as the motion of particles, because it needs to follow some crystallographic restrictions. So particle is a discrete portion of solid but not atom. And as we have seen that the motion of the particles, how they orient with the direction of the propagation of the waves themselves will decide the what is that wave is, the whether it is a longitudinal wave or a shear wave. So the longitudinal wave is also known as irrotational wave. So for finite, infinite and semi-infinite media, so this is called as dilatational wave. And also in seismology it is known as primary wave. For seismology, the wave study is very important for earthquakes, and this is called as primary wave. So we will discuss what is that longitudinal wave is, and for simply if we want to say that this is the motion of the particle in this wave is along the direction of propagation of wave. And for shear wave, which is also called a transverse wave or distortional wave, and for seismology it is called a secondary wave or SH or SV wave. Surface waves are known as Rayleigh wave, and then interfacial waves, or it is called a Stoney wave, love wave, that is the waves in layered media, bending or flexural waves are found in bars and plates. Okay, let us discuss about the longitudinal wave now. The longitudinal waves are the waves which have the particle motion along the motion of the wave. So I will write it here. The motion of the particles is back and forth along the direction or parallel to the direction of wave propagation. So then it is called a longitudinal wave. Basically we can call them the velocity of the particle, which you represent as Vp, is parallel to Vw, which is the wave propagation velocity. So let us consider an example. So this is a long cylindrical bar. We are hitting that bar with a hammer. So what will happen is that these particles, if we hitting with the hammer, this particle velocity will be along this rod from left to right, and similarly, as we know, this wave propagation is also from left to right. This is a compressive wave. And as you know from our earlier discussion, the velocity here we can express it as square root of the ratio of Young's modulus to mass density. And if the wave is compressive, if the wave is compressive, then Vp and Vw will have same sense, and I'll tell you what is that same sense. And then if it is tensile, the wave is tensile, Vp and Vw will have opposite sense. So that means in the previous case, as this is a compressive wave, so what is happening here is the velocity of the wave propagation or the wave propagation is from left to right direction, and even the particle velocity is also from left to right direction. So that's why it has the same sense. And if the wave is tensile, that means if you are giving a tensile loading here, the velocity of wave will be anyways in this direction, because we are the disturbance starts from this end of the bar. So velocity of a wave, oh sorry, that's not Vp, the velocity of wave will be in this direction, Vw, this Vw, and the velocity of P, the particle velocity, as we are pulling this or giving a tensile loading here, so velocity of particles, that is Vp, will be in the opposite direction. So that's why we wrote here that this is in opposite sense. So that is the difference between the compressive wave and tensile wave. They both are longitudinal wave here. And if you want to discuss about shear waves, so shear waves is the velocity of particle is perpendicular to the velocity of wave propagation. So in this case there is no resulting change in density, and the longitudinal strains epsilon 11, epsilon 22 or epsilon 33 are 0. So we will see with a diagram, we will explain this with a diagram. Suppose we have again we are taking a cylindrical bar, so we are giving some torsion at the left end. Let's say torque is applied on the left end, and we are keeping a clamp at a few distance, at a little distance away from the torque, the application of the torque. So this portion will develop some torsion here, and when we release the clamp, so when we release the clamp, so the wave will propagate. The wave will propagate in this direction. So this is velocity of wave or velocity of wave propagation from left to right. But as you can see that this is a torsion, and the particle velocity will be perpendicular to the direction of this axis of this cylindrical bar. So that's why it is also called as distortional or transverse wave. Okay, so this is all about the shear wave, and we will now discuss about the third wave, that is surface wave, surface, or it is called as Rayleigh wave as well. So here we have some diagrams. The first one is nothing but the shear wave that we discussed in the just last slide, and the second diagram is surface wave or Rayleigh wave. So we can see the difference now. The Rayleigh wave is analogous to water surface wave. So when we throw a stone in a pond, and the whatever wave we see, that is a surface wave, and that is in the water, and whatever the surface wave we encounter in solids, that is we call as a Rayleigh wave. So that's analogous to the water surface wave. So one can think that the shear waves and Rayleigh waves may be similar from these two figures. So what happens is, if we go inside, this is, let's say, the surface of the water, this is surface of the solid, it can be water, but this is, in this case we are taking a surface of the solid. So this face is the top face is the surface of the solid. So when we go deep inside, actually here in this case the wave is propagating from this side, and this portion is now undisturbed, this right hand side portion. So the wave will propagate this way, wave propagation. So if we go deep inside, the wave is not prominent. So here at the surface, Rayleigh wave is prominent, and then it will damp down when you go inside. You can see these lines. So this is very prominent at the surface, and then when you go inside, it is damps down, and here it is, very little wave can be seen in the deep inside. But for shear wave, we can see that it's a little different, and this is the particle velocity here is perpendicular to the direction of wave propagation. So wave propagation in a slender bar and semi-infinite body. So we will now discuss what is the difference if we take different objects. So if you take a thin long bar, or what will happen to the waves, as we have seen that the longitudinal wave will propagate in a thin bar. But if we take a semi-infinite body, so what will happen, we will see from this picture here. So as we have already discussed, that if you take a hammer and hit a long thin bar, so you will see longitudinal wave here. But if you take a semi-infinite body, and hit with a hammer, this is the semi-infinite body. That means so this is the body, it's semi-infinite. So if you hit the hammer in the semi-infinite body, so what will happen is one longitudinal wave will propagate, and that front of that longitudinal wave will look like this. It will propagate in this direction, it will look like this, and then even a shear wave will also propagate. But the difference is, the shear wave, the particle velocity will be perpendicular to the propagation of this wave. So this is longitudinal wave, and there will be a shear wave, but the difference is that the particle velocity will be perpendicular to the wave propagation velocity, and there will be third wave is this surface wave on the surface. surface wave. So this is generally, if we, sorry, this is longitudinal. So if we take a semi-infinite body, so this is a semi-infinite body, you can see that majorly three types of waves are present: longitudinal wave, shear wave, and surface wave. And in this case, for a thin bar or slender bar, we have only longitudinal wave. The other waves are very negligible. So we can see that we talked about longitudinal wave, we talked about shear wave, we talked about Rayleigh wave, and we will talk about now we don't discuss much about the interfacial love wave or bending waves. So interfacial waves or Stoney waves are formed when two semi-infinite media with different properties in contact. Then a wave, spatial wave forms at their surface interface, forms at interface. And then love waves are that is in layered media, important in seismology. As you know that Earth's surface is composed of different layers. Composed of different layers. So these waves are seen in Earth's surface in seismology, and the horizontal component of this displacement is significantly larger than the vertical component. And then bending wave or flexural wave, this involves propagation of flexure in 1D or 2D configuration. So comparison of different waves, so we want to compare their amplitude and their how they vary in a half space. So that is half space. Again we are taking, that's a semi-infinite body. Semi-infinite body. So this is, let's say, the source of disturbance. So the longitudinal wave, this is the front of the longitudinal wave. So if we draw the amplitude, this is just a schematic just to show the relative amplitude. If you draw the amplitude, so you can see here it will be thin, and if you go along this side, this will be a little thicker. So this is the amplitude for longitudinal wave, and the shear wave is a little bit complicated. So it looks something like this. This is, we are drawing the relative amplitude, the shear wave. So you can see that at some part, so we have zero amplitude for shear wave, and then the Rayleigh wave will be on the Rayleigh wave will be in the surface. So just it is important to mention that the velocity of this longitudinal wave is the highest, is fastest, and then comes the shear wave, and then the surface wave, or we can write it as Rayleigh wave, is the slowest one here. And we will see how it decays at the surface. At the surface, the longitudinal wave decays at r to the power minus 2. It is inversely proportional to the radial distance, the square of the radial distance, and similarly for shear wave also it is r to the power minus 2, but in this direction deep inside, so this is decay as r to the power minus 1, and here also it is decays at r to the power minus 1, and that means it is slower, the decay is slower in this direction deep inside, and then on the surface it is faster. And also for the Rayleigh wave, the decay is very slow, r to the power minus 0.5, which means the Rayleigh wave will travels to much longer on the surface. So, and this actually, as I told you, this is the relative amplitude, and we will show you another aspect of it, this the percentage of energy for these three waves. This is important, percentage of energy for these three waves are so for Rayleigh wave it is the highest, 67%, and for shear wave this is 26%, and for longitudinal compressive wave it's just 7%. All this calculation is for a Poisson's ratio of 0.25. So you can see that the Rayleigh wave has the most energy is carried out by the Rayleigh wave. So we will demonstrate with a helical spring the difference between the transverse wave and the longitudinal wave. We have a helical spring like this. This is the original spring, and we will demonstrate here in this slide by drawing it, but in a real life experiment will also follow. My TAs will show you a demonstration of this whatever we will discuss here today. So for a longitudinal wave, so if we give this moment back and forth, so what will happen is, so there will be compression and there will be expansion, and then again will be a compression and there will be an expansion. So this is compression and expansion, and this will give us the wavelength lambda. Similarly for transverse wave or shear wave, we can give the motion up and down for this, and then what we'll get is the spring will look like this. Sorry, this diagram is not very clear probably, but this string will look like this. So this if you see the wavelength lambda is this distance. So this is transverse wave and longitudinal wave. Anyways, we will discuss this with a real experiment demonstration. So that's the end of this lecture. Thank you.